is going to be the Algebra 2 section 9.6 video. This one's a little bit different. I didn't have my full smartboard to really make a video, so I'm trying this app on the iPad using some notes made from last year. So hopefully this works out. But basically, let's see here. Okay, so first off, these are, let me erase this a little bit up here. I have a couple problems that must have been from the previous section that I just want to show you real quick. So they must have been questions asked last year. I'm thinking they're from section 9.5. If you want to just verify real quick, this was number 42 and 43 kind of worked out. So again, it looks like one of the problems with the compound interest or using E. So check out number 42, number 43 if you want to see the work on that. Those are written right there. You can pause the video and check those two out. So this section is kind of the same idea here. Whereas that section, the example was usually like putting money in a bank account, you earn interest and whatnot. So this can be kind of related to any type of exponential growth. Or decay. So it looks a lot like what we saw at the beginning of the chapter where it was y equals a times b to the x. So you can see these two formulas here for growth as y equals a, same thing, the initial value. And then this 1 plus r, if they give you a rate. And then the exponent, instead of calling it x, we're just calling it t. And for decay over there is y equals, again, a, the starting value, times 1 minus r. So this would be like if they say something's growing at 12% per year, or something is decreasing by 8% per year. Those percentages would go in for r. And you could figure out how much there would be of whatever we're talking about a certain amount of time later. So let's look at a couple examples. First off, and I'm gonna keep this on the bottom so I can kind of scroll up. Let's say you purchased a car in 2013 for $12,000, and the value is expected to decrease by 16%. Okay, so since that value is decreasing by 16%, the thing is you need to write r as a decimal. So 16% of course would be 0.16. And sorry, that's sloppy. I don't have a stylus. I'm using my finger there. The r value is going to be 0.16, and since it's decreasing, this is the decay example, so we're going to use the starting value again times 1 minus the r value. So 1 minus the 0.16, and that gets us 0.84. So that's our equation there in red. Okay, again, 12,000 was the initial value. It's decreasing by 16%. Okay, so if you think about it, that means it's worth 84% of what it was the year before. That's where the 0.84 comes from. It's 1 minus that r. And then t, of course, will be the number of years after 2013. Okay, and let's say we want to estimate the value of the car in 2020. So we just need to figure out how many years went by. So from 2013 to 2020 would be 7 years. So our exponent becomes 7. And this just becomes a little calculator problem. Make sure we do our order of operations first, where we need to do the exponent first. Okay, we should get an answer of $3,541.08. Okay, so that's when something is growing like per year or per month. It's called a discrete growth or decay, and it's kind of like if you want to think about. So let's think this for this car example. The car would have been worth $12,000, but then as soon as 1 year was up, then it just instantly dropped down to 16% less. Okay, but throughout that year, technically with this model, it didn't change. It's kind of like a big jump from 1 year to the next year, and then the next year would be worth less, then the next year would be worth less. But a lot of times, things grow or decay continuously. Okay, like constantly, like smoothly throughout. Like if you think about a gas gauge in your car, it doesn't go from full down to 3/4 like instantly, right? It kind of goes through everything gradually and continuously. So with those types of situations, the problems are a little different. The formula is still y equals some initial value a times the natural log base e. Okay, a times e to the kt. And again, t is always going to be time, just like it was before. K is the new thing here. That's something we're going to have to actually solve for. It's called a constant. In each problem, it's going to be different. And if you notice for the decay formula, the exponent, the K is a negative number. Okay, so it's still some initial value A times this E. Again, remember E is approximately 2.71 to the negative KT power. Okay, and again, K is that constant that varies from problem to problem. Okay, so let's see this in action. Okay, let's scroll down here. So let's say the population of rabbits in a region has been growing exponentially. In 2005, there were 225 rabbits. In 2013, there were 1,475 rabbits. Okay. Now, this was a type of problem we did at the beginning of the chapter, but we didn't do it as a continuous growth. We figured out what was the B value, like per year. Okay, remember we would plug into y equals a times b to the x. A would be the 225, the starting value. The x and y would come from the 2013 and the 1475 rabbits, and we would solve for b, and that would still work, and that would get you close, and it'd actually be a pretty similar modeled equation. But if we're assuming continuous growth, okay, it's going to be a little different. We're going to have to use this y equals a times e to the kt power. Okay, so let's start plugging some things in here. So first off, down there in purple, the 1475, okay, that's the ending value, that's the later value, that's y, equals a, which is what we started with, 225. Okay, again, e we know it's 2.71, but we're just going to leave it as e. Remember, that's a number kind of like pi. It's like, we write it as a symbol, but we know it's really a value. It's not a variable. And then t, of course, is 8. 8 years have gone by from 2005 to 2013, and k is the thing we're solving for. Okay, so I'm going to write the exponent as 8k instead of k8. And now we need to go ahead and solve this thing for k. So we got to figure out what is the growth constant here. So I'm going to start out in red here, divide both sides by 225. Okay. So that's going to get me, when you do the division, so down here now we see this 6.5556. That's just the division problem down here. On the right side of the equation, the 225 cancels out. We're just left with an e to the 8k power. Okay, so now we notice our variable is part of an exponent. So I guess it's going to make me erase that stuff before we scroll down here. Okay, so how do we solve for an exponent? We take the log of both sides. Or we write it in log form. Okay, it's log base e of the 6.5556 equals 8k. Okay, so remember log form, that's big in this whole chapter. Anytime when you're solving for an exponent, change to log form. That's really going to be the way to go. And then if we remember log base e from last section, that's the natural log. Your calculator has the LN button. The natural log of 6.5556 equals 8k. And we'll just simply divide both sides by 8 to try and solve for k. So you can enter it in your calculator, making sure that you have the parentheses around the 6.5556. Because again, you're just taking the natural log of that number, close parenthesis, and then divide that answer by 8. And that should give you your final answer here, or that should give you your k, and then we can at least write the equation. So the k value turns out to be about 0.235 in yellow there. That's the ln of 6.5556 divided by 8. And now we can write our equation. We know that it's y equals, again, the initial value was given to us at the beginning, the 225. E just stays in as E. We just found K, so that gets plugged into the formula right there. And then, of course, we want to leave T as a variable so we can plug in anything we want. Okay, and then the assignment which you will do in class will be page 548, numbers 6 through 8, 12, and 18. Okay, and they should be very similar. Just kind of be careful and think about if it's... I'll give you a little hint here. Number 6 and 7, they appear to be more of a continuous growth, like the one we just did. Number 8, I'm looking at that one, says the value of something is depreciating 20% per year. That's going to be more like the first one, where you're not using E as the base. You're going to use the 1 minus R. Let's see, let me look at number 12 real quick. Assuming that the value of the condo will appreciate 5% per year. So again, that one's more of a discrete. That's the 1 minus r. I'm sorry, appreciate 1 plus r. And then 18, let's see, they bought a house 10 years ago, it's worth 191, if it's a steady growth rate. Yeah, that one's going to be more of the, not the continuous case with the E, but more of just the growth per year, the more discrete case. Alright, there you go. That is section 9.6.